To keep this quick and brief so you can get to the work, and I'm not going to take up too much of your time. So these notes follow the POGO that we did and go along with, and you might want to look at some of the pages in the book as well to get a good idea of what's going on. So we talked a little bit about what chemistry was today in class, and I wanted to expand on that a little bit. So chemistry is what's called the physical science as opposed to something like biology, which is a life science, since it describes the physical world. And we're going to be making ourselves concerned with matter, which is anything with mass and volume. So we need to have mass and volume to be matter. And volume itself is not an important key measurement of mass of the material, but mass is, because mass measures the amount of matter. So it's a little bit of a circular definition, but mass is really what's important. That tells us how much we got. Volume is dependent upon a lot of different things, as we'll see. The other thing that chemistry involves is the study of energy, and we're going to be looking at how energy and matter interact with each other. And we'll talk more about energy later on in the course, but energy is the ability to either do work, so you want to get something done with it, or to release heat. You want to warm something up. And energy interacts with matter, and it's going to be released or absorbed during chemical changes. And we'll talk about chemical and sometimes physical changes as well. We'll talk about those. We're going to see those tomorrow. Now, we talked about pure substances in the POGL, and a pure substance always has a specific composition. And because it has that specific composition, that means it has very specific properties, both chemical and physical properties. And we're going to talk about properties in our next class as well. Elements, as we saw, are pure substances. So there's two types of pure substances. An element is a pure substance composed of only one kind of atom. And again, we saw that today. And an atom is what we call the representative particle. So there's that particle again. Basically, you've probably learned about this representative particle of an element. It's the smallest particle that you can break an element down into and still retain the properties of that element. So somebody in one of the classes brought up quarks. Quarks, yes, they're particles as well. They're subatomic particles. But even though quarks make up atoms, a single quark doesn't retain the properties of the element that we're looking for. In terms of breaking them down, and this is something we'll talk about when we talk about early scientists, they can be broken down chemically. It can't be broken down, cannot be broken down chemically or physically. And so once scientists got down to something that couldn't be broken down, they were pretty sure they had an element. Related to elements are compounds. And again, compounds are pure substances, and they contain only one kind of, now there's going to be a new word for you here, one kind of molecule, which you guys are used to talking about, like a molecule of water. But there's a new kind of word for a compound I'm going to introduce to you, and that's called a formula unit. A formula unit we'll talk about in a moment. Molecule we'll get to as well. In a compound, the ratios of the atoms are constant. So we always have a 2-to-1 ratio of hydrogen to oxygen in water. We always have a 2-to-1 ratio of oxygen to carbon and carbon dioxide. And so we call that the law of definite proportions, meaning that a compound always has the same proportions of the elements. And again, we'll talk more about that in Unit 4, I believe it is, when we start talking about the early scientists and how they talk. Maybe it's Unit 3, I don't remember, how they started understanding what elements and atoms were. Compounds can be broken down, but only chemically. They can't be broken down by physical means, such as heating them up gently or filtering or anything like that. So, for instance, I can take 2 water molecules and I can break them down into 2 hydrogen gas and 2 oxygen gas. That's a chemical breakdown. We have a change in the particles, and we'll talk about that in our next class as well. Now, what is a molecule? Molecule, you've seen this term before. A molecule is a representative particle of a very specific kind of compound, and we're going to call that compound a molecular compound. These are compounds like water. Here's water, carbon dioxide, here's sucrose. These are compounds that have a discrete group. Discrete meaning it can stand by itself. Two or more atoms, non-metal atoms. So when we talk about the periodic table later on in the week, we're going to see it breaks down into metals and nonmetals. And for a molecule, it's going to break down into two or more nonmetals. And these nonmetals have what we call a covalent bond. And that's the kind of bond you're used to seeing, like with H2O having the lines between them. Those are the covalent bonds. So all of these guys are molecules. Now, there's another kind of compound, and that kind of compound is represented by sodium chloride, for example. And we're going to see more about this in the next lesson as well. In these compounds, the formula unit, it's a single unit of a formula. Think of it like that. But it's the lowest whole number ratio of what's called ions in an ionic compound. And an ion is simply an atom that has a positive or negative charge, meaning that it's either lost electrons or gained electrons. And that's going to be important because ions and atoms have different properties from each other. They're changed, they're different from what they were before. In ionic compounds consist of a metal and a nonmetal together. And in the case of sodium chloride, sodium is the metal, chloride is the nonmetal. And we're always going to see the metal written first and the nonmetal written last. And in these compounds, the ions are held not as individual molecules, but in long-range crystal structures, a long-range crystal lattice. And you can't hold a discrete molecule of sodium chloride in your hand. You'll hold a crystal of sodium chloride that has lots and lots of these formula units repeating on. And we represent sodium chloride as sodium NaCl with those implied subscripts of 1 because the formula unit, if you break it down, the formula unit is just one sodium, which is the small purple spheres, and one chloride, which is the large green spheres here. Now, mixtures. Mixtures are not pure. By definition, they're not pure. They are physical combinations. And if I ask you to define them, please don't tell me that a mixture is a mixture. Don't define it with itself. It's a physical combination of two or more pure substances. So mixtures are not pure. And in the next lesson that follows our activity in the next class, we're going to learn how to separate these impure mixtures from each other. In the mixture, each substance retains its original properties, both chemical and physical properties. And this is going to lead into our lab on Wednesday as well. And within a mixture, you can have any ratio. So the law of definite proportion doesn't hold. I could have 100-to-1 hydrogen to oxygen gas, but that doesn't make it a compound. It's not going to make it into water. And there'll be a lab later on that we will explore this ratio and how to determine the ratio that these elements exist in. Most materials are mixtures because there's this concept called entropy. Entropy favors mixing. Entropy is just a measure of how much disorder you have. And we'll talk a lot more about entropy later on in the class. But anytime we have things mixed together, it's because of this concept of entropy causing that mixing to be favorable to happen. Now, there's two kinds of mixtures. The first one, homogeneous mixtures, where the prefix homo means the same. And in this case, the same means one, what we call a phase. This phase is a uniform composition phase. It looks smooth. It almost looks pure. It looks pure and smooth, but it's not. if we were to look at it under a good microscope, or if we look at it with a particle diagram, we're going to see the different particles that are in there. These are more difficult to separate because they are so well mixed. And things like solutions. Solutions are things like salt water, Kool-Aid. Those are going to be difficult to separate. We have ways of doing it, but they're more difficult to separate. And as a liquid, these are transparent. They may be colored, but you can see through them. This is only for liquids, though. And the other thing that we think of as homogeneous mixtures are metal alloys. And we saw one of those in the lesson, metal alloy, where we had copper and zinc made brass. Now you can't see through these, but these are metal alloys, are sometimes called solid solutions. And these are also homogeneous mixtures. So we'll be seeing a bunch of these during class as well. The other kind of mixture, and this is actually the most common kind, is heterogeneous. And that prefix hetero means different. And so in these, we have two or more different uniform but separate phases. And in this case, they're easier. These kinds of mixtures are easier to separate because the distinct phases are easy to make out. You can separate them using fairly easy techniques, such as, so some examples, we got slurry. So any opaque liquids, this would include things like milk, blood, milkshakes. Oh, there's milk right there, sorry. Salads. So salads, in this case, salads is going to be easy to pick out. Now, I go to the restaurant, I don't like radishes. So if they give me a salad with radishes, I don't have to send it back. I can easily pick it out. Unlike soup, if they put salt in soup, I can't really pick the salt molecule or the salt ions out. So easy to pick out. Okay, so salads, trail mix, chocolate chip cookies, where the chocolate chips are easy to see in the dough. All right, so these are the kinds of now I can't call them substances. Substances only refer to pure materials, so let's call these materials. These are the kinds of materials that you will run into this year in class. All right, so I hope this covers it for you. If you have any questions, please let me know, and we will go over the homework in class on the next day. All right, take care, and I'll see you then.